So next thing we'll talk about is Markov chains. And to do this, we'll look at an example, which is weather in Seattle. So 3 outcomes for weather: sunny, overcast, or rainy. We're not going to look more closely than that. And tomorrow's weather depends on today's weather. So if today's sunny, tomorrow could be sunny, overcast, or rainy with different probabilities. If today's overcast, it's not going to be sunny, but it could be overcast or rainy. If today's rainy, tomorrow's probably going to be rainy, but small chance it could be sunny or overcast. This seems pretty reflective of what actually happens in Seattle. So we can take this information and put this into a diagram. There's sunny, overcast, and rainy. And this diagram is what we call a Markov chain. Okay, so if today's sunny, 50% chance of it still being sunny, 30% chance of it being overcast, 20% chance of it being rainy. Today's overcast, don't necessarily have to draw the line if it's 0, but 0% chance of being sunny, 50% chance of being overcast, 50% chance of being rainy. And if today's rainy, 50% chance of tomorrow being sunny, 5% chance of tomorrow being sunny, 10% chance of tomorrow being overcast, and 85% chance of it being rainy. There's your Markov chain, a good visual for how to get around this graph. Every time you travel along an edge, so this is actually a directed graph, every time you travel along an edge, that's 1 day. Okay, this is difficult to look at, so we can also make a transition matrix. Which will be the matrix we multiply by going from one day to the next. And we'll just put all this information, which is the same as this information, in a matrix form. So first column will be for sunny. If today's sunny, then 1/2 chance of sunny. You could do decimals here, it doesn't matter. 3/10, I started with fractions, so I guess I have to keep going with fractions. And 1/5 for rainy. That's copying that. Next, overcast will be 0, 1/2, and 1/2. And then rainy will be 5%, 10%, 85%. So that's 1/20th, 1/10th, and this is 17 over 20. Probably should have done decimals. However, that is the transition matrix. And then you can start at any state. So let's say today is sunny. It is the summer. Sunny would be sunny with probability 1, overcast with probability 0, rainy with probability 0. And then what we can do is we can start to multiply. So tomorrow, V1 is going to be A times V0. And then we multiply, we get 1/2, 3/10, 1/5. As our original information said, 1/2 chance of being sunny, 3/10 chance of being overcast, 1/5 chance of being rainy. But this is not interesting. What is interesting is that we can keep predicting days in the future. V2 is going to be A times V1, or A squared times V0. And now we can multiply this matrix again. Let's see what we get. We get 1/4 plus 1 over 100. So 20, okay, I'm going to go to decimals, 0.26. And then we get, let's see, 3 over 20 plus 3 over 20 plus 1 over 50. So this is a total of 3/10. 0.3 plus 1 over 50 is 0.02, so 0.32. And then these better add up to 1, so the last one is going to be let's see, what is that, 5/8, so 4.2. Check the math of the multiplication, should come out to 0.42. Great, so I know that if today is sunny, in 2 days, I have a 26% chance of being sunny, 32% chance of being overcast, 42% chance of being rainy. And I could keep doing this. But multiplying matrices is hard. So let's just look ahead and see what happens. Let's look at A to the 9. And I'm just going to keep track of 3 decimal places. Pre-computed this, 0.073, 0.192, 0.734, 0.073, 0.191, 0.736, 0.074, 0.191, 0.735. Oh, this is interesting. And actually, if I keep multiplying, so like these columns all look pretty similar. If I continue and get higher powers of A, you know, I just looked at like a to the 34, but if you look higher, they all look like this. So now, and actually, I could have actually gone a lot more than 3 decimal places at this point. All 3 columns kind of converge to the same column vector. 735. And I could have gone more decimal places than this. So what is happening? Well, if you think back to linear algebra, especially if we take this V naught 1, 0, 0, so that's just going to be the first column, we get, so what in Markov chains is we call this a steady state vector. After 30 days, 90 days, 1,000 days, 7, 4, right? 0.191, 0.735, that was our first column of A to some big power. Basically, after any number, after a large number of days, if we started sunny, we have 7.4% chance of still being sunny, 19.1% chance of being overcast, 73.5% chance of being rainy. This actually does seem pretty representative of Seattle weather. And because all of these columns look the same, which may not be true, depending on your original matrix A, it actually doesn't matter if today was sunny, today was rainy, today was overcast. Eventually, we would always tend towards this distribution of weather. And if we remember back to linear algebra, we call this an eigenvector. What's actually happening here is A times some vector V, we'll just call this V, no superscripts, is going to give you V back. So that is an eigenvector with eigenvalue 1. Remember, an eigenvalue in general was AV equals lambda V. Okay, so next week we'll review more linear algebra and we'll be able to talk more in depth about Markov chains.